everyone. Today's webinar, we will be talking about mechanical component failure rates for static versus dynamic operation. Before we get started, can everybody please make sure that your mic is off? Now, there is a question and answer tab at the top of your screen. Please make sure that you use this at any time. Because this box will cover up part of the screen, I will answer the questions, as many questions as time allows, at the end. So if you have a question on a certain slide, we can turn back to it through the slides at the end if you need to. My name is Lauren Stewart. I graduated with a BSME from Virginia Tech. I started my career in design and manufacturing before coming to exida to work in functional safety. Here I work as a safety engineer in our consulting end of the business, working with our mechanical clients. I also work on research here at exida, publishing books and papers, and I also do some speeches and I work with our database. exida is a functional safety company that is worldwide. We were founded in 1999 with 2 offices and have grown to many around the world. exida is a systems consulting, product test, and assessment agency rich with functional safety and security expertise and experience. We have just opened 2 new offices in Houston, Texas, and Vietnam to add to all of the others around the world. exida focuses in 4 main industries: OEM, which is management support, development support, and certification tools; system design, which is FSM setup, SIL verification, and tools. We work with end users in SIL and device selection, SIL verification, tools, and security audits, and engineering contracts, which is tool, competency development, and CFSE, CFSP programs. exida does a lot of different things, but they are all focused on functional safety and cybersecurity. We do systems level consulting, which includes process safety, alarm management, control, and security. exida has an accredited certification group. We do more functional safety certifications than any other group in the world, which includes functional safety, control systems, cybersecurity, and network robustness. For the process industry, we do a lot of training. This includes process safety training, control system security, on-site and off-site, web and security development. We have engineering tools that help people implement safety life cycle, including Excellentia, FAMIDAs, and SCA, which we'll get more into. And we also invest heavily in research, data, and finally, exida operates the CFSE, CFSP program. Taking a closer look into exida's tools, we have FACTS, which is Process Hazard Analysis, Hazard and Operability Studies; Excellentia, which is SIL Verification, SIL Selection, SRS, and Proof Test Generator; the SCRH Viewer, which is Safety Equipment Reliability Database; SIL Alarm, which is our Alarm Rationalization Master Alarm Database; and SIL-STAT, which is collection and analysis of operation and maintenance safety data. exida has created a lot of reference material. I'm proud to say exida has authored or co-authored most of the industry references for automation and safety and reliability. Now we can get into the heart of our presentation: mechanical component failure rates for static and dynamic operations. The first key point we will make in this presentation is that the failure rates of certain mechanical components used in solenoid valves, actuators, and valves vary substantially depending on operation. For example, seals such as O-rings have fundamentally different failure modes when used in applications with frequent movement being dynamic versus applications with infrequent movement being static. The second key point we will make is exida has accumulated over 100 billion operating hours of field failure data, primarily in the process industries, which was used in recent mechanical failure research. This webinar explains some results from this recent exida research, where failure rates and failure modes of several mechanical components were established. First, we should define static and dynamic. Static is defined as stationary or fixed. So, in mechanical applications, this would be considered low-demand mode application. Dynamic is defined as energetic, capable of action and/or change, or forceful. In mechanical applications, this would be considered high or continuous demand applications. I started my research into the difference in static versus dynamic operation failure rates by investigating how mechanical failure rates are determined. There are 4 possible ways, which are FMEDAs, which stands for Failure Mode Effects and Diagnostic Analysis, End User Field Failure Studies, Manufacturer Field Return Data Studies, and cycle testing data. There are positive aspects and negative aspects for each method. FMEDAs identify failure modes within the device, which could relate those failures to the operation of the safety instrument and function. The positives for FMEDAs would be that they can provide detailed and complete information. It is a predictive tool, which does not require a multi-year lab time to gather statistics. But negatively, it depends on component failure mode and failure rate data. FMEDAs are specifically used for safety in both high demand and low demand applications, so it would be considered safe for any use. End user field failure studies. The positives are that it is real data. Their negatives are there are variations of the amount of data collected. There are different definitions of what people consider a failure, and it categorizes and merges technologies. Manufacturer field return data studies. Once again, as a positive, it is real data. Negatively, the calculation methods vary widely from company to company. We cannot know what percentage of actual failures are returned, and also, once again, everyone has a different definition of the word failure. And finally is cycle test data. Cycle testing is the accelerated motion testing until either a failure or a given number of cycles is used to simulate years. Cycle testing assumes that the application has a constant dynamic operation. Cycle testing is safely used for high demand or continuous demand applications only. As I just mentioned, cycle testing or cycle test scaling is used for dynamic or high demand applications. The reason for this is because it assumes that premature wear out is the dominant failure mechanism and no other failure mechanisms are significant. I started my research into the differences between static. To illustrate these methods, we can compare the failure rates of solenoid valves found by each method. Starting at the top of the chart, we have 2 FMEDAs, one of a solenoid valve and one of a spool valve. Next, we can compare the values of an actual field data study from a chemical industry. After that, we move on to the ARETA data, published failure rates, and as you can see, it is the highest number on our chart. Next, we move on to 2-cycle test result of solenoid valves. As you can see, these are the lowest failure rates on this chart by far. Finally, we will look at manufacturer's study, being warranty data, which falls directly in the middle. As the example shows, cycle test data has a much lower failure rate than other methods, which is fine for a continuous demand application. But be careful using cycle test failure data. Some certificates use cycle test data as their only method of finding failure rates. This assessment is not valid for typical low-demand process applications. Cycle test results are 40 times lower, or more than 40 times lower, than the other methods of calculating failure rates, including field failure data. Low-demand modes of operation have their own application hazards. While cycle testing is an acceptable failure rate prediction technique for a high-demand or continuous demand application, but for using it for low demand is dangerous. Low-demand applications can generate failures that high-demand applications cannot develop. While in an inactive state for a long period of time, issues such as stiction can transpire. So what is stiction? Stiction is a combination of static plus friction. The resistance to start motion usually measured in the difference between the external force being applied in order to overcome the static friction and the force to maintain movement between two contacting or working surfaces. It can result from corrosion, cold welding, breakdown of lubrication, the build-up of deposits, chemical reactions, or the breaking down of sealing components. So now, who really cares, or should I say, who should care about stiction? Well, Exida's study started by researching stiction to determine the maximum time period before stiction impact failure rates. This is the maximum time period for scaling cycle test results, which led us to find much more. In our research, we discovered that stiction becomes significant after 1 week and maxing out after 275 hours of rest time. Therefore, users should never scale cycle test results beyond 200 hours, since 275 is the absolute maximum. In finding this max time period for scaling, we have discovered that improvements in safety and reliability can be obtained with stroke testing. As you can see, this is a typical 5-3 spool valve. Some solenoid valves can have multiple to many O-rings or seals, which create possibilities to cause problems with sticking or binding or stiction. Although stiction is not well documented, there is plenty of evidence to suggest that it increases with the length of time the valve is stationary. We'll look into 4 cases of this knowledge. First off, we will look into the expert knowledge. These are people who are technicians or engineers who routinely work on the valves. In a study shown, we found that they all say stiction occurs after a week or more, not being able to give us an exact time though. O-ring manufacturer guidelines say that the valve can be stationary between 1 week and 1 month. Delay between cycles or stiction plateaus at about 300 hours. There is an experimental study that we found that was conducted on lubrication thicknesses in magnetic thin filmed disc. This set the equilibrium rest time increasing as stiction increases to a plateau around 275 hours depending on the lubrication type. And finally, ISO 13849 says that a valve must be operated at least once per week or once per shift to ensure the intended function. From this multi-source of evidence, we can conclude that it is a rule of thumb. O-rings stiction increases with the valve inactivity and reaches a maximum value at approximately 275 hours. Stiction's impact is shown. Failure rates result when forces are insufficient to move mechanical parts as designed. This can be caused by environmental variables impacting the rate of friction buildup. Therefore, stiction is treated as a stochastic variable for failure rate analysis. Once stiction is broken via this movement, friction buildup starts over. So bringing us back to the impact of static versus dynamic failure rates, we take a look at an example. Here is a femita of a solenoid valve broken into the failure rates of dangerous failures due to stiction, which we look at as lambda d stiction, which is 103.7 fits or failures per 10 to the 9th hours of operation. It was also broken down into lambda d non-stiction detectable, which are the failure rates not due to stiction, which are detectable through operation. And this is at 84.3 fifths, and lambda d non-stiction undetectable, or the failures of not due to stiction, which are not detectable, and that's at 1.9 fifths. For a static application, all the dangerous failures, lambda d stiction, lambda d non-stiction, detected, and lambda d non-stiction undetected are added together to form a total lambda d of 189.9 fifths. But if stiction is not an issue, as in a dynamic application, the lambda d stiction can go to 0, taking away the majority of the dangerous failures. This graph shows just what we are talking about. So for the same solenoid valve, just in different applications, static versus dynamic, we can get a drastically different number of failure rates. Once again, this shows that the lambda d total is adding the lambda d stiction, the lambda d non-stiction detectable, and the lambda d non-stiction undetectable for a static operation. For a frequent dynamic movement, we do not have to add in the lambda d stiction. So we only have lambda d non-stiction detectable and lambda d non-stiction undetectable for 86.2 fifths. As we saw from examples and experts, static versus dynamic failure rates can and will be dramatically different. We suggest from this knowledge never to use cycle tests, results, and data unless the application moves the mechanical device at least every 200 hours. Cycle testing was created for a continuous demand application only. And if you have a low demand application where the mechanical device does not move at least once every 200 hours, use either femita failure data or expert analyzed plant failure data. Now is the time where I'll look at the question and answer part. So if you have any questions or comments that you have not written down yet, please do so now. Or you can email me at lstewart@exida.com, and I will answer every email as soon as possible. For more information, you can also look at all of our free web seminars at our website, exida.com. We also have white papers listed there. You can also get more information on our safety automation elements list at that link, saelonline.com. And we have books at both exida.com and isa.org. So let me go up here and look at what questions we have. Okay, so for our first question is asking, I see the mode of operation is shown as low demand. So the certificate is a low demand certificate with cycle testing. Let me go back and see which slide we're talking about. Here we go. So yes, this is a certificate using cycle testing, and it is shown, as you can see here, in low demand mode, and it assumes 10 demand per year. I can see how this is confusing. IEC 61508 defines low demand as no more than 1 demand per year. So we're going to move past this certificate, and this must be a mistake. Let's see the next question. The next question we have is, you only get down to 86 bits. Why not lower like in the previous cert? Let me see here. Okay, as you can see, the frequent dynamic movement, which would be the same as the dynamic movement for cycle testing, in our example, does get down from lambda D non-stiction detectable to lambda D non-stiction undetectable as 86.2 bits. This is assuming 10 demand, or the cert is assuming 10 demands per year, which is 876 hours between movements. So this looks like the cycle testing was scaled way beyond 200 hours. So it gives you a lower and invalid number. So please be warned of low and not usable numbers. This, even with frequent dynamic movement, should not be scaled that low. Are there any other questions? Next we have, is there a place where all the failure rate data was compiled? And yes, there is. We compiled all the failure rate data at exida into our 2H database. I actually have a blog on our website that explains all about our 2H database and how it is used and all of that information. So if you would like to go ahead and see more information on 2H or our database of failure rates, please go to our website. I see someone has their hand raised, but there is not a question. If you would like to ask a question, you have to go ahead and type it in. Yes. We will be posting a recording of this webinar. Sorry, the question was, can we kindly share slides? Yes, we will be posting a recording of this webinar on our website, so you will have the slides and my voice talking over them anytime you'd like to. So if you go on later this week on exida.com, you will be able to see the slides. And finally, a question is, how do you detect the detectable failures? What kind of testing and diagnostics are considered here? And I'm assuming it's staying on this slide. There are different detection, there are different ways to detect diagnostics. Each time we do an FMEDA, we consider the own company's diagnostics. In this case, it could be a stroke test, a partial valve stroke test. There are many different, an automatic partial valve stroke test. There are many different ways to detect diagnostics and detect stiction, and we will take each situation and each company into consideration when we go through the diagnostics. Are there any other questions? And that's all the questions that I currently have here. If you do have any other questions, please feel free to email me at any time. Once again, my email is lstewart@exida.com. And once again, we have our webinars and our blogs on our website, so please feel free to access them at any time. Thank you very much for attending today's webinar, and I hope you all enjoyed it.